this chapter, we'll be looking at exponents and logarithms. In this lesson, we'll be reviewing logarithms and then looking at their derivatives.
All right, everybody. So in this lesson today, we are going to review logarithmic functions, and by the end of the lesson here, we're going to look at the derivatives of the logarithmic functions here. And they're actually, it's really good. I mean, yesterday you were introduced to the exponential function, and you saw that the derivative of the exponential function is just the exponential function, which is wonderful. That's amazing. Today you're going to see a whole bunch of other derivatives here that are related to it, and they're all, at this point here, they'll be just slightly more complicated than the exponential function. So it's some good news. They're easy derivatives coming up. But before we get there, let's take a look at logarithms. Let's make sure you remember some of the properties that are going to become important in this lesson here. So first of all, remember that if you see that you got 2 cubed is equal to 8, we know that's true. The logarithmic form of that is to say log base 2 of 8 is equal to 3. Okay, so a logarithm, like an exponential function, has a base. Okay, but the logarithm is equal to the exponent. Okay, a logarithm is an exponent. So this, basically, the logarithm identifies what exponent would I have to put on 2 so that the result is equal to 8. There's the answer, 3 there. So in general, b to the x equals y, if that's true, base to the exponent equals y, then the logarithmic form of that is log base b is equal to x, and then I put the y inside the logarithm. That becomes the argument of the logarithm. Okay? Now, you should recognize these laws of logarithms. Some of you would have just finished this lesson in your other grade 12 class. So the timing is wonderful here. So this is picking up right where that would have left off. So the product law. If you've got a product within a logarithm, and it's really important that you understand that this is within a logarithm. This is not log of x times the log of y. That's not multiplication between two logarithms. It's multiplication within a logarithm, becomes addition between two logarithms. Okay? And that actually makes perfect sense, because when you multiply two powers together, a to the x times a to the y, the result is a to the x plus y. When you multiply powers, you add the exponents. Well, and remember, a logarithm is an exponent. So there you go. The quotient law says that if you've got the log of a quotient, the result is the difference between their two individual logarithms. And again, that makes sense because a to the x divided by a to the y is a to the x minus y. And remember, a logarithm is an exponent. So the division becomes subtraction there. The power law, and this is probably the one that you utilize the most when you were first learning logarithms, because it makes this an incredibly useful tool for solving exponential equations. But that you've got that power, if you've got a power in the argument, you can bring that exponent down and multiply it through. And then again, that makes sense, because if you've got a to the x to the y, this is the same as a to the xy. Okay? The power of a power, you just multiply those two exponents together. And now finally, the change of base rule. Okay, and I'm going to zoom in on this one just so that we're really clear on this. If you've got the log base b of x, I can convert that to any base I want, such as a, by making this the log base a of x. So I put the argument up here, and then the log base a of b, and I put that down here. This is one of the first laws that we end up looking at when we first introduce this concept of a logarithm. But having said that, it's one of the first laws that people forget once we start to apply it. Okay, so now we're just going to look at some applications here. So solve for y in the log base 4 of 8 equals y here. Now, I say solve for y. The truth is it's already been solved for here. The question is, how do you get that? One way of doing this is to convert this log base 4 of 8 equal to y into exponential form. So 4 to the y is equal to 8. And then we can rewrite those both as powers of 2. Okay, in which case this becomes 2 to the 2y equals 2 cubed. And once the powers are the same and the bases are the same, I can set the exponents equal to each other. Now, this is not canceling the bases. There's no such operation. Okay, there's no such thing as canceling the bases. Because I've actually heard people describe it like that, but that's not what we're doing here. We're just saying that if they're equal, And if the bases are equal, then the result is the exponents must be equal. And then you can just divide that 2 over to get y equals 2/3. Or you could write this as the change of base formula there. Remember that the thing that we're looking at here was the log base 4 of 8. And we could make that log base 10. Remember the common log, if you don't write the base there, the base is 10. Common log of 8 divided by the common log of 4. Just put that in your calculator and you'll get 1.5. Same thing. Oh, hold it. Ha! That's awesome. I screwed that up. In my notes here, this should have been 3 over 2. Sorry. They are the same now. So perfect. Let's take a look at another one here. Solve for x in the log base 3 of 2 minus x is equal to 3. Okay, now this is going to be in the notes there. First thing you probably want to do with this is, let's flip the page. Okay, convert this into exponential form. So it becomes 3 cubed is equal to 2 minus x, the argument of the logarithm. 3 cubed is 27. And then when you rearrange things, you're going to get that x is equal to negative 25. Now, does that make sense? Is it possible for x to be negative 25? Because remember, you cannot take the log of a negative. We're going to talk a little bit more about that later on in this lesson. But you can't take the log of a negative. But that's okay, because if you plug negative 25 into this, you end up with 27, and that's fine. So we're totally okay with negative 25 in there as a value for x. Okay, now another rule here or application that you need to be familiar with here is, how do I go about doing something like this? How do I evaluate these two logarithms added together here? I don't know what the log base 12 of 9 is. Now granted, I can go to my calculator and do it. Okay, but assuming we don't do that, plus the log base 12 of 16, one way to do this is to combine these two terms into one term using the product law. Now we're going to talk about combining in just a moment here, but addition becomes multiplication. So then we end up with the log base 12 of 9 times 16, which is the log base 12 of 144. And if you're familiar with logs, if you're comfortable with logs, you'd recognize that the log base 12 of 144 is just 2. Okay, because 12 squared is 144. And remember, the logarithm is going to equal that exponent there. So 12 squared is 144, log base 12 of 144, 2. Okay, now let's take a look at this guy right here. We want to rewrite this as one log, okay, in one term here. When I teach this normally, the rule that I try to employ here is it should be 2 steps to 1 log, okay? 2 steps to 1 log, and I try to push that idea, 2 steps to 1 log, and the reason I do that is because it's very common for people to look at a logarithmic expression and create more logarithms by trying to distribute it here. But when you're dealing with a bunch of logarithms, like in a logarithmic equation, you want to get it down to 1 logarithm. If the number of logarithms increases, you're doing it wrong. Okay, so let's take a quick look at this. Remember, addition becomes multiplication, subtraction becomes division here. Now, the first thing that I want to do is get rid of the coefficient. Okay, in essence, I'm applying the order of operations. I want to deal with multiplication first, then I'll deal with addition subtraction. So first thing I'm going to do is move that 2 up, and you can see that in this step right here. I move that 2 as the square on the C, and then, and this is really important to make sure that you get this done correctly here. I have struggled for years teaching this course, teaching diploma prep and whatnot, watching students apply the laws of logarithms and getting the wrong answer. And it bothered me trying to figure out why people are doing this incorrectly. But the reason they were doing it correctly, it finally occurred to me, is they were doing it backwards. When you apply the laws, the order of operations, and you've got a bunch of addition subtraction, you always go left to right. Always left to right. And so this is what you're supposed to do here. When we combine these logarithms, we're still going to do it by following this thing through left to right here. So log base 2 of a plus the log base 2 of b is going to be the log base 2 of a times b And then minus the log base 2 of c squared means we're going to divide by c squared. Essentially, if you've got any logarithmic term that is positive, that argument ends up in the numerator. And if it's negative, okay, if the term is negative, that argument ends up in the denominator. Now, just to maybe expand this one step further, let's just say, what if this was, and let's make this the log base 2 of d plus the log base 2 of a plus the log base 2 of b, let's say minus, and I'll move that up right now, c squared. So it's the same question here. Let's say that this was the question. What does this equal if you put it into one logarithm here? Well, this will become the log base 2 of, and I really think you should just follow this rule quite diligently here. If there's a negative in front, what this means is I'm dividing by that argument. Now, I don't know quite what I'm dividing it into here, but I know that's going to go in the denominator. This will go in the numerator, this will go in the numerator, this will go in the denominator. And so that would be log base 2 of ab over dc squared. It should always be 2 steps to one logarithm when we're combining a bunch of logs together. Okay, anyway, that aside, let's take a quick look now at logarithmic functions, okay, the graphs of these things. And I know this should be review for everybody, but there's a point to this. Okay, there's a point to this, and you'll see it in a few minutes here. So let's say we're looking at the log base b of x. Remember that this is the inverse of the exponential function. Okay, the logarithmic function is the inverse of the exponential function. Okay, in other words, when you take the inverse here, when you take that y equals b to the x, when you find the inverse of it, you get x equals b to the y. This is the logarithm. However, it's not written in a good form here, so what I do is I convert this to the logarithmic form, y equals the log base b of x. And that's more useful to me. This is correct. This is the inverse. This is more useful. Okay, remember graphically that the inverse function is the reflection over the line y equals x. Okay, and we get it. And I know we just did this here by switching the x and the y. And so here it just summarizes it here. The exponential function y equals b to the x becomes the logarithmic function, or sorry, it doesn't become, but is its inverse is y equals the log base b of x. Now, because they're inverses of each other, remember that they're going to sort of cancel each other out here. Now, I'm just giving an example. If you've got the square root of x squared, the answer here is x, because those two operations are inverse of each other. In the same way here, if you've got b to the log base b of x, the exponential function here and the logarithmic function cancel each other out, and that becomes x. Same way, if you've got the log base b of b to the x, the answer again is x, because they're inverses of each other. Okay, now let's take a quick look at the graph here. So here's the exponential function, and here's its inverse, the logarithmic function, and again, notice it is the reflection over the line y equals x. Now in this case here, we're assuming that b is greater than 1. Okay, there is a restriction here when we start talking about logarithms here, particularly the base can't be equal to 0, and it's got to be greater than 0. Additionally, the base here can't be 1. Okay, that's would lead to a weird definition with the logarithm here. So you've got some restrictions on the base here, and if you recognize that, you'll notice that we talked about those kind of restrictions being applied to the base of the exponential function as well. So there's really nothing new here. Now let's take a look at some of these properties. With the exponential function, notice its y-intercept is 0 and 1. It's got a horizontal asymptote at y equals 0. If you take the limit as x goes to infinity, now let's zoom out here, make sure we can see the graph here. If you take the limit as x goes to infinity, okay, the result is infinity. If you take the limit as x goes to negative infinity, dropping down this way, we're going to approach 0. We talked about that the other day. Now, let's talk about the logarithm here. It's got an x-intercept of 1, 0. It has a vertical asymptote here at x equals 0. If you take the limit as x approaches infinity, the logarithmic function, it actually does go to infinity, okay? It does it extremely slowly. Okay, logarithmic growth is really, really slowly. You think about the common log. When you take the common log of 1,000,000, the result is only 6. If you take the common log of 1,000,000,000, you're at 9. You haven't even gotten to 10 yet. It grows really, really slowly, but it does grow. Okay, and it does go off to infinity here. Now, I've got this written down wrong here, and we need to fix this here. This is not the limit as x approaches negative infinity, because the thing is the graph isn't defined there. This should be approaching 0 from the right. As you approach 0 from the right, the graph drops to negative infinity. Okay, so that should look more like that. Sorry, little edit there. Okay, these are really old notes. I made them in a hurry a long time ago. Okay, so little edit there. Now let's keep going. Now, we're going to introduce this idea of a natural logarithm. So we've just spent some time talking about the properties of logs, about the graph of the logarithmic function here. Now we're going to talk about natural logarithms. And I just want you to understand that this is exactly the same. It has all the same properties as everything that we've just been looking at. It's just that now the base is a little different, and we're going to go back to what we looked at yesterday. We're going to use the base e. Okay? So remember, this is the exponential function, base e. We are now going to look at its corresponding inverse, base e. So there it is right there. Y is equal to the log base e of x, but we used a different notation for that. Okay, ln of x. And actually, you will see, hold on one second here, that shows up on your calculator. There's your log button, there's your natural log button. Okay, notice that when you press second button here, second function on the calculator, usually you're accessing the inverse function here. Same thing here, the inverse of the natural log is going to be e to the x. You can see that from your calculator. Now, in this case, ln stands for Logarithmus Naturalis. I don't know why, but anyway, it's Latin. Why not? Okay, here we go. Next. So y equals ln is the inverse of y equals e to the x, but if you graph those functions here, notice this doesn't look any different than what we did before. Okay, but it's because it's just the only thing that makes this unique here is the base. The functions still behave exactly the way you'd expect an exponential function and a logarithmic function to behave. What's special is the fact that the derivative of this function right here is equal to the value of the function at any given point. Okay? So, and I've got these properties over here, and this was written out correctly here. If you approach x from the, 0 from the right, you go down to negative infinity. If you approach infinity, it goes up to positive infinity here. Now, we're going to do just a series of quick questions here that are really just designed, okay, the intention here, the total intention is just to get used to the natural logarithm. Okay, so let's take a look at the natural logarithm of e to the x here. Now, you should realize that these are inverses of each other and that the answer should just be x. They should cancel each other out here, but let's say you don't see that. Then what you do is you're going to say that, okay, if I don't know what that is, I'm going to let it equal y. And then what I'll do here is I'll convert this to the exponential form. So the base here is e, so it'll become e to the y equals e to the x. E to the y equals e to the x here. The bases are the same, so the exponents must be the same. So y, whatever I said that was equal to, that must be equal to x. And so there we go. The natural log of e to the x is x. Exactly the same thing here. E to the natural log of x. These are inverses of each other. The result here should be x. But let's assume right now that you don't know what it equals. You're not familiar with that. So e to the natural log of x is equal to y. What I can do is I can take the natural log of both sides. Okay? And when you do that, when you take the natural, well actually that's, yeah. The best way to think about this actually is probably not the way I've got it written down here. The easiest way to deal with this is to think of it like this. The issue that we're having here is that exponent. Let's just call the exponent y. So we're going to let the natural log of x equal y. Okay. So what I'm looking at here is now e to the y. I've rewritten it. Now let's convert this to the other form here. The base is e, so this becomes e to the y is equal to x. And see, once you write it like this, it becomes really quite clear how this works here. When you look at the exponent, it spits out this relationship here, but that's what I was looking for, right? That's the relationship I was looking for, so this is equal to x. It basically tells you immediately, in fact, in many ways, that little proof happens so fast, it's hard to see. But the e to the natural log of x is just x. Now we're going to answer some other questions here that I think should be equally as clear. The natural log of e, well, this is base e, and the rule is still the same. If you've got log base a of a, the answer is 1. And you would have known that from an earlier course here. So the log base e of e is going to be just 1. And actually you see that worked out over here. The natural log of 1. Okay. Again, same sort of thing as before here. If you've got the log base b of 1, we know that that was equal to 0. Well, it doesn't matter here that we've got a base e. That rule is still going to be the same. The answer is going to be 0. Again, if you don't know what that is, you can set that equal to y and then convert forms, and you get e to the y is equal to 1. And now just think, what exponent on that e is going to produce 1 as a result? And the answer is 0. So the natural log of 1 is going to be 0. Now let's take a look at some solving so that you can see just how straightforward this really is here. The natural log of e to the 3 minus x here. Now, a couple of ways you could approach this. What we want you to do here is realize that this is base e. So to start off with here, you're going to convert this to the exponential. E to the 8 is equal to e to the 3 minus x. And then you've got two powers that are the same. The bases are the same, so you can make the exponents equal to each other. And when you solve for x, you get negative 5. Of course, another way of looking at this is you've got log base e of a power of e. So immediately, these two are inverses of each other. They cancel each other out. You're just left with 3 minus x is equal to 8. And from there, you can also get that x is equal to negative 5 relatively quickly. Solve. The natural log of x minus 1 is equal to 2. Again, what we want to do here is get used to converting forms here. This is base e, so this becomes e squared is equal to 3x minus 1. So add the 1 to both sides, divide by 3, and we get this. This is the exact form. So if you were asked to do this on an exam and give the answer in exact form, that's where you would stop. Okay? But that's, if you go to your calculator, you'd see that that's approximately equal to 2.79. Find the domain of y equals the log base 3 of x squared minus 1. Now we're going backwards a little bit here. It doesn't really matter what base we use here. This could be a natural log base 3. It doesn't really matter here. The point that we want to make with this one here is to remember that whatever's inside here has to be positive. So now I'm just going to do the work down here. What I need is x squared minus 1 to be greater than 0. Not even or equal to 0. It's got to be greater than 0. If it's not positive, I can't take the log of it. Now, just think about what this is. We've solved stuff like this before. This is one of the things we looked at near the beginning of this course. Remember, this is like x minus 1, x plus 1. So I've got two x-intercepts here at negative 1 and 1. And note that this is a quadratic that opens up. So it's going to open up like this. So where is this function positive? Where is it above the x-axis? Well, it's above the x-axis over here and over here. So the domain of this thing will be where x is less than negative 1 and where x is greater than positive 1. Whoops. Okay, that's your domain. And it doesn't really matter what the base is. That could have been a natural logarithm as well. Okay, and that's what you're seeing, sorry, at the top of the next page here. Now, another way of writing that, by the way, is to state that the absolute value of x is greater than 1. Okay, that actually has the exact same meaning as this right here. And hopefully you remember that from Math 20, where you would have seen that last. Okay, so here's some questions that you can look at later. There's more to cover here. Besides that, this is what you're really interested in. You want to know how to take the derivative. Because remember, if you get through this exam and you're like, wow, I never took a derivative once, you did it wrong. Okay? You got to be taking the derivatives here. Now let's see how this works here. And actually, this is really a nice lesson here. We're gonna go back to some information that you had before and utilize that. So for those of you that are sitting there cringing because you're like, oh, he's gonna make us do first principles on a logarithm. No, I'm not. Here we go. Consider the function y equals the natural log of x here. Now to take the derivative, try changing forms first. Okay? So we're going to take our y equals the natural log of x. We're going to make this e to the y is equal to x. Okay, now this is the exact same thing as this. Okay, they are identical, different forms, same idea. But I can take the derivative of that pretty easily. So you can take the derivative implicitly. The derivative of e to the y will be e to the y times y primed. And the derivative of x is just going to be 1. So we get e to the y primed equals 1. Now we just need to solve for y primed. Now that means dividing by e to the y. But here's the trick. What does e to the y represent? Got to go all the way back up to here. E to the y is x. So the derivative of the natural log is 1 over x. Well, that was awkward, particularly because they hung up before I got to the phone. Anyway, so we conclude that if y is equal to the natural log of u, remember some function of u, then the derivative is going to be 1 over u, okay, u primed. So you'd have to, because remember, this is just telling you the chain rule here, okay. Now, there is something to consider here. When we go back up to this, I'll just do it over here. Just a little discussion that I want to have with you. In fact, it might even be later in my notes, but I'm going to do it right now. If you've got the natural log of x here, remember that the domain is that x is greater than 0. Now, when you take the derivative, you're getting 1 over x. The domain here is that x, okay, can't be equal to 0. Now, I hope you're remembering something that we did a while ago here. When you take a derivative, the domain should actually get smaller. It shouldn't be getting larger. Okay, so one of the things you gotta think about here is that when you take the natural log of x, okay, we are assuming. Okay, so when you take the natural log of x, there's the domain here. This is going to carry through. Okay, so we're going to get y primed equals 1 over x. We're going to have to ignore that, and the domain here has to carry through because the derivative can't be defined someplace where the original function wasn't. In this case, the relationship, though, is such that it looks like it is defined places where this one isn't. So you're going to need to be very vigilant to watch that domain. Now, this is going to become an issue, an even bigger issue in the next chapter. This is not such a big deal for us right now, okay? But it will be a bigger issue in the next chapter, and we're going to start to include absolute values in these logarithmic functions to accommodate for that. Anyway, let's just apply this for a little bit here. We're going to take some derivatives here. So if we've got y is equal to the natural log of x cubed, we get y primed is equal to 1 over x cubed. There's the derivative of the natural log. And then we multiply by the derivative of what's inside, the x cubed, so it becomes 3x squared. 3x squared over x cubed becomes 3 over x. Now notice, another way you could have written that is y equals 3 times the natural log of x, and then the derivative is just 3 over x. Oh, looky, looky, that was more fun, wasn't it? Let's keep going. We're going to take the derivative of this right here. Notice that's all inside the natural logarithm here. So you can do this in a couple of different ways. So first of all, you could multiply that through and make this the natural log of, what do we got here, 3x squared, what is that, minus 2x plus 15, so it's going to be plus 13x minus 10. You could think of it like that, expanding that out. And then when you take the derivative of the natural log is 1 over that. And then you would multiply by the derivative of what's inside there. Okay, so bring down the 2 and then you get the 13 there. There we go. And it would look like that. That works great. Or, and just like I showed you in that previous question, or you could use the laws of logarithms first here to separate that out into addition. And actually the derivatives here are so much more straightforward, because this is just going to be 1 over x plus 5 times the derivative of the denominator, which would just be 1. This would be 1 over 3x minus 2. And then you would multiply by the derivative of what's inside there, and you just get the 3 coming out. And so the result is you get 1 over x plus 5 plus 3 over 3x minus 2. Then what we can do is add these two fractions together, and notice that you go exactly right back to where we started here. Now this might seem like a little bit more work than the previous method here, but you're going to see probably on Monday just how useful this method is, okay, in a different context. Here, I just use this example here just to show you that it doesn't matter how you approach this, whether you use the laws of logarithms first to take the derivative, or you do it later, okay? Oh, and okay, right here, sorry, this is that little discussion about the domain here. Often what we're going to do here is to get around that problem here is when we talk about the natural log. Now this isn't always going to be true, but oftentimes you'll see us put absolute values around what's inside there. Because if you put absolute values around that, then you end up with a domain here where x can't be equal to 0. Because of the absolute value, I can put negatives in there because the absolute value make it positive, and then I'll take the log. And then when I take the derivative, I get 1 over x, and again the domain is x can't equal 0. And so that absolute value symbol there kind of fixes that problem. Okay, anyway, like I said, not a big deal right now. We will come back to that later. In the last section, remember this from the other day? Oh, that was fun. Hey, look at that. The derivative of b to the x was b to the x times that limit right there. That was awesome. Now we're going to take a close look at this limit right here. Now I know right now you're probably looking at that going, oh, do we have to? Actually we do, and it turns out this is a lot simpler than it first looks here. First of all though, in order to understand what we're about to do, you need to know that e to the natural log of b is b. They are inverses of each other. Okay, that these two are exactly the same. Now, it might make sense to you to go this method to say that, yeah, if I've got e to the natural log of b, I can simplify that to get b. But the truth is, we're going to use it this way. What we're going to do is we're going to take a look at the derivative of b to the x, and we're going to make that the derivative of e to the log of b to the x. Okay, so we're converting the base into that e to the natural log of b. This is still just b. And then we can make this the derivative of e to the x times the natural log of b. So we're just going to multiply the exponents together. But now it's this exponential function. Now I'm looking at y equals e to the x natural log of b. Think about what the derivative of this would be. Well, it's going to be e to the x natural log of b. And then you multiply by the derivative of the exponent, which is just the natural log of b. Okay? So, because remember, natural log of b is just a number multiplied by x. If you've got some sort of number like y equals ax, the derivative is just a. Well, in this case here, that a is just the natural log of b. And remember that e to the x natural log of b, where did I get that from? Well, that was b to the x. And so the derivative of that exponential function is going to be the exponential function times the natural log of b. It turns out this ratio right here is the natural log of b. b to the h minus 1 over h. And now, if you want to check that, just go to your calculator. The natural log of 2, oh, look at that. It's about 0.69. The natural log of 3, look at that. It's about 1.10. Okay? Awesome. So if y equals b to the u, then y prime is equal to b to the u times the natural log of b, and then you got to include the u prime there. Okay, it's good, just again for the chain rule. Now, one more thing here, and then I'm going to let you guys, we're going to do some practice here. I'm just going to give you guys this rule now. You can prove it in a very, very similar way here, but if you've got the y equal to the log base b of u, some function of u, So now it's a logarithm with a different base here. The derivative becomes 1 over u, and this time you put the natural log of b in the denominator, okay, times u primed here. So that's the rule right there. It's a very, very similar rule to what we just saw here. It's combining the two rules here. So it's 1 over because of the logarithm, and then you put the natural log of b in the denominator, and there you go here. So just to take advantage of this, if we've got y equals x squared times the log of x, we want to take the derivative of that, okay? First of all, you're going to use the product rule because you got two powers here. Two functions here. X squared, the derivative of x squared is 2x times the common log of x. And now the derivative of, we have to multiply by the derivative of the common log of x. So x squared times 1 over x. And then notice the base here, if it's not written as 10, so I would have to write that as the natural log of 10 down there. Okay? And then x squared over x simplifies, and so you get 2x log, whoops, I lost the x there. 2x log x plus x over the natural log of 10. Okay, you just got to throw that down there. So again, just so that you're really clear on this, if I've got log base 3 of, let's say, x squared, okay, the derivative here is going to be 1 over x squared. You got to be really clear on that. 1 over x squared, whatever is inside that log, boom, down there. Times the natural log of 3, the base, put that in the denominator. And then you would multiply by the derivative of what's inside, because there's a set of brackets there with a logarithm that's implied. And then it just so happens that these things simplify a little bit, so you would cancel, so you'd get 2 over x natural log of 3. Okay? Now, on the other hand, if you've got y equals 2 to the x squared, if you've got a different base here, then when you take the derivative of it, you get 2 to the x squared. Okay? Remember, the exponential, the derivative is itself. Now, in this case, because the base isn't e, I have to multiply by that natural log of the base. That's that limit. And then you multiply by the derivative of the exponent, which is 2x here. Now, but in this chapter, you got to be a little careful because notice I've got a power of 2 here and I got a power of 2 here. This is like 2 to the 1. And when you multiply two powers together, you have to add the exponent. So 2 to the x squared plus 1 times x times the natural log of 2. Now that will be on that exam, okay? There will be multiple choice questions here where you might take the derivative like this, list it all out here, but there's that additional factor of 2, or that function there, and I have to add the exponent. So you got to be watching for that. Okay, here's another assignment there, something you can look through. Spend some time to work on those, and we'll talk about it later.